All right, hello, and we are going to be dealing with the last two sections in one video because they're all modeling questions. So within exponential functions or logarithmic functions, we find them everywhere in nature. And one of the nice things is because they're found everywhere in nature, there's been a lot of studies using them, and we can develop different models that estimate what's going to happen in a certain situation. So the first one that I'd like to talk about would be exponential growth. So exponential growth is exactly what it sounds like. And remember, if you recall that the function is graphed as such, then after you get to a certain value, let's say t on the x-axis, and then we're going to call this n of t on the y-axis. So once t is greater than 0, meaning positive values, we start to see this skyrocket in terms of population. And like I said, this happens all over the place. And models do one thing for us. They provide us with an idea of what's going to happen. It doesn't mean that it's going to happen, but at least it provides us with a good picture of what could happen, okay? So, like I said, the first one I'm going to start with here is exponential growth. And the model that we have for exponential growth is right here. So if the initial size of a population is n sub 0, or n naught, some people call that n naught, but it's just n sub 0, and the doubling time is a, then the size of the population at any time t is given by n of t equals n sub 0 times 2 to the power t over a, okay? So n of t is going to be your final population. Remember, this n of 0 is the initial population, and then this letter a is going to be your doubling time. All right? So basically, this is going to be more or less just substituting into the model. The only interesting thing is we're going to be able to answer questions that we never answered before, like how many hours will the population be, or how long will it take for the population to be this large or this small or something like that. So here's an example right here. And I'm going to read it real quick. If you want to, pause the video and then write it down, and then you can read it along with me. But we got, under ideal conditions, a certain bacteria population doubles every 3 hours. Initially, there are 1,000 bacteria in a colony. So part A, find a model for the bacteria population after t hours. Part B, how many bacteria are in the colony after 15 hours? And then finally, and I'm going to put a star next to C, because this is a question that we really couldn't answer before, which is, after how many hours will the bacteria count reach 100,000 bacteria? Okay? So the first thing, we're going to do part A. So I'm just going to kind of scroll up here a little bit. So part A is find a model for the population after t hours. So remember, our initial model that we have from the definition is n of t is going to equal n sub 0 to t over a. Now, if we want a model that will estimate the bacteria population at any time, we're going to have n of t equals. Now, our initial population comes from the problem, so n sub 0 is going to equal 1,000. So this would be 1,000 times 2 all raised to the t over 3. And if you're wondering where I got the 3 from, let me zoom out and let me scroll up here a little bit. Get out my little highlighter. We know that the bacteria population doubles every 3 hours. So A is going to equal 3. All right, and here's our answer for part 1. So it's a nice model. Now, if you wanted to derive this model, in other words, if you wanted to figure out, okay, how do we get this equation, you would need differential equations for that. And that is Math 253 or 251, I think, where you would solve a problem that looks something similar to this on the right-hand side. All right, and you'd have to solve this. This is a differential equation. So you would need calculus in order to do this. But for now, for us, what's really nice, the model's already there. We just kind of substitute in what we need. Part B. Part B asks, how many bacteria are in the colony after 15 hours? So this is just a straight up substitute in 15 for T. So 1,000 times 2 to the 15 over 3. So n of 15 is going to equal 1,000 times 2 to the 5th. We know 2 to the 5th is 32. And then after 15 hours, we will have 30. Oh, I was going to put dollars. We're going to have 32,000 bacteria in this population. All right, so there's part B. And then, like I said, with this last part C, this is the problem that we really couldn't, could never answer before. So I'm going to just write it out. So after how many hours will the bacteria be 100,000? Okay? Now, common sense tells us when we compare part B to part C, it took 15 hours for the bacteria to get to 32,000. So we know our answer has to be larger than 15, okay? So what we're going to do here is this. We're going to rewrite our model, okay? And we're going to identify what we're solving for. Well, after how many hours is T? And notice T is in the exponent of our model. So we're going to have to figure out a way to get that letter T down with everything else. Also, we know that we want a final population of 100,000. So our model is going to look like this. It's going to be 100,000 equals 1,000 times 2 to the T over 3. So the first thing I would do here is just isolate my exponential by dividing both sides by 1,000. That's going to give me 100 equals 2 to the T over 3. Now, we need to get this letter T down here with everything else. And we know that if we use our properties of logs, we can do that. So what I'm going to do is I'm going to take the log of both sides. And by doing that, I can pull this T over 3 out front. So we get the log of 100 equals T over 3 times the log of 2. Then, if I want to, I can simplify a little bit. The log of 100 is 2. Finally, I'm going to divide both sides by the log of 2. All right, that gives me 2 over the log of 2 equals T over 3. And then multiply both sides by 3 to give me T. Sorry, let me write it like this. 6 over the log of 2 equals T. And get out a calculator. Type in 6 divided by the log of 2. And that's going to be approximately, rounded to 2 decimal places, 19.93. So at 19.93 hours, we will have 100,000 bacteria. All right? And that's really how every single exponential growth problem looks like, okay? Whether it's exponential growth in a bank account or exponential growth with another famous example would be like a rabbit population. Especially when you get into differential equations, you're gonna go over wolf and rabbit populations and how they interact with each other. And for example, if there's a lot of rabbits, then there's going to be a lot of wolves that are going to eat all the rabbits. But eventually, the population of the rabbits goes down, which means there's not enough to eat. So some wolves, unfortunately, will die. Some wolves move away. So then the population of the wolves goes down. Now that there's less wolves, the rabbits can increase their population again. And it's a cyclic equilibrium type situation between those two. All right. So I'm going to go ahead and pause the video and get set up for our next exponential model. Okay, so here's our next exponential growth model, and it's relative growth. Now, the difference between relative growth and the one that we just did, let me scroll back up so you can see it. This is doubling time, okay? So the population doubles over time. What we're looking at here is relative growth. This is growth without bounds, okay? Sometimes you may hear it called or referred to as Malthusian growth, which means you have limitless resources and you just allow things to happen. Just growth just continues and continues and continues, and there is nothing preventing it from stopping, okay? So you can see that this is a little bit different from the previous. So a population, that experiences exponential growth increases according to the model. N of t equals n sub 0 e r to the t. So this is instantaneous. All right, it just keeps going and going and going and going and going, and nothing stops it. Okay? Now, if we wanted to, we can model this formula with the previous one just by saying r equals 0.02, because that would be the relative growth. It would double, or 2% of the population would double over time. All right? So real quick, just to kind of write things down, n of t is the population at time t, n sub 0 is the initial population, r is the relative growth rate, t is going to be time. So a simple example would be something like, how long will it take for an initial investment of $5,000 to double if the growth rate of the investment is 10%, okay? So here, all we really got to do is kind of just label everything. We know our model is going to be n of t equals n sub 0 e to the rt. And going from left to right, our population at time t, well, in this case, it's not really a population, it's money. But if you think of dollar bills as a population of dollars, then we would know that we want this money to double. So I want 5,000 to 10,000. So n of t is going to be 10,000. Our initial investment is going to be 5,000. E, now we know the growth rate. The growth rate is the investment rate, which is 10%. So this is going to be 0.1. And what we need to do is solve for t. So once again, I'm going to isolate the exponential by dividing both sides by 5,000. All right, and I'm trying to get out my calculator here real quick because I'm going to need it. So 10,000 divided by 5,000 is going to be 2 e to the 0.1 t. Now I'm going to take the natural log of both sides. And the reason why I do that is I want to take this exponent right here and pull it out front. So I get the ln of 2 equals 0.1 t. Now remember, I could write the natural log of e, but by definition, this equals 1. So it's nothing more than just the natural log of 2 equals 0.1 t. And then I will divide both sides by 0.1. And I'm going to use my calculator real quick. So just give me a second because I'm kind of off screen using my calculator here. So we have the natural log of 2 divided by 0.1 is 6.93 years. Okay, 6.932 years, which if there are any investing people in the audience, this number should look kind of familiar, okay? Because there is this thing in investing called the rule of 72, which means your money doubles approximately every 72 months, which is approximately, 72 months is equal to 6 years, but I'm saying approximately because it depends on the interest rate. But on average, your money will double basically every 6 years if you're investing it. All right. So we're going to look at another model right now. So I'm going to go ahead and pause this video. All right. So the next model we're going to be looking at is radioactive decay, which we both know this as half-life. And this model is set up basically the same exact way that everything else was. All right. I'm going to use different letters though, because for some reason your book chooses different letters. But the amount of a substance is going to equal how much you initially started with times e to the negative RT. Now, remember, if our exponential is negative, it's going to look something like this. It's going to come down. It's at what we call exponential decay. All right. So if we wanted to derive our half-life formula, which we totally can do that using basic algebra, the idea behind this is, you have, let me get rid of this arrow here. We have an initial amount of substance that we're starting with. What we want to know is, when will the ending amount be cut in half? All right. So the first thing we're going to do is cut it in half. All right. Then we're going to go ahead and we're going to solve for t. So give me 1 second here. So we're going to assume that we started off with an initial amount of 1. Or if you want to think about it as 100%, that's fine. But we're just going to assume that we start off with 1 gram, 1 kilogram. It doesn't matter what the unit is. So this is going to give us 1/2 equals 1 e to the negative RT. All right. Now just to clean this up, it's going to be 1/2 equals e to the negative RT. Then we're going to go ahead and take the ln of both sides. By doing that, I can take this exponent and pull it out front. We know by definition the natural log of e is going to equal 1. So you get the natural log of 1/2 equals negative RT. And then if we divide both sides by negative r, we're going to get negative ln of 1/2 over r equals t. Okay? But this is where you got to be careful, okay? Because you got to remember this negative we can actually put back up there, all right? And I'm going to write it like this first. And to make this exponent positive, all I'm going to do is just apply my negative exponent rule. And by doing that, I flip this over to give me r over, sorry, my bad. Wrong way around. I flipped the wrong thing. The ln of 2 over r equals t. All right? And if you get out a calculator real quick, let me see, where's my calculator at? There it is. Put it in scientific mode. If you have 2 and you want to find the ln, it's 0.693. So if you've ever looked this up in textbooks, your half-life of something is always 0.693 divided by the rate at which it decays. So like I said, you can look that up in a book, Normally you see it in a chemistry book or something like that, but that's what it is. All right. So let's go ahead and let's look at an example. So I'm going to pause the video so I can write down the example. All right, so here's our example here. So polonium 210 has a half-life of 140 days. Suppose a sample of this substance has a mass of 300 grams. First thing we're going to do is find a function that models the mass remaining after t days. Then we're going to find the mass remaining after 1 year. And then finally, we're going to find out when will the mass be 200 grams. Okay, so let's look at part A. And let's start off by writing what we know, because we want to find this function here. So we know our initial population, or the initial mass, is going to be 300 grams. We also know the rate at which this decays. So R is going to equal the natural log of 2 over 140. This is our half-life right here. We'll call it the half-life rate. I think it might be a good way to say it. So our model is going to be m of t equals 300 e to the negative 0.00495 t. Now, the natural log of 2 over 140 is equal to negative 0.00. Actually, sorry, it's equal to 0.00495. Okay? Next, part B. Find the mass remaining after 1 year. So the mass after 1 year, and since we got to be careful here because they gave this to us in days, the half-life was given to us in days, we're going to have to use the numerical equivalent of days in a year, so 365. So m of 365 is going to equal 300e raised to the negative 0.00495 times 365. And if you take out your calculator and you do that, you're gonna get about 49.265 grams. Okay? And then finally, part C. When will the mass be 200 grams? Well, in this situation, you're going to get 200 equals 300e to the negative 0.00495 t. Okay? So from here, what we have to do is we're going to have to isolate the exponential first. So 200 over 300 is 2 over 3, which equals e to the negative 0.00495 t. Now, we're going to take the natural log of both sides. So I get the ln of 2/3 equals the ln of e to the negative 0.00495 t. That is going to allow us to take this exponent and pull it out front. So we get the natural log of 2/3 equals negative 0.00495 t times the ln of e. We know the ln of e goes to 1. So what we can do here is just divide both sides by negative 0.00495. And that's going to give us t equals approximately 81.9 years. So if you just have 300 grams of polonium just sitting there, it's going to take about 81.9 years for it to go from 300 grams down to, or I'm sorry, not years. Forgot. This is in days. It's going to take 81.9 days to go from 300 grams down to 200 grams. All right? So I think we have one more model here. I'm going to go ahead and pause the video. All right, so here's our last exponential model that we're going to be looking at, and it's one of my favorites. It's Newton's law of cooling, all right? And Newton's law of cooling is really cool because you can use this to find the temperature of anything cooling off in an environment. You can use it to actually determine when somebody died. If you just know a couple measurements, that's it. So forensic scientists use this all the time. So Newton's law of cooling is defined as T of T, which is this is going to be our final temperature. So the final temperature is going to equal the initial temperature, okay, multiplied by e to the negative kt. K in this situation is going to be a constant, and it actually has a special name. Sometimes they call it a proportionality constant, but it's basically the rate of cooling, okay? T stands for time, obviously, and then T sub S is going to be the temperature of these surroundings. So, you know, if you're inside a air-conditioned building, it could be 72 degrees or something like that, okay? Now, I do have an example for it, and it's a very simple example. We got a cup of coffee, and I've never had a cup of coffee in my life. So you coffee drinkers, maybe you can let me know when the safe temperature is to drink coffee. I would think it'd be about 100 degrees Fahrenheit, but what do I know? I don't drink coffee. So a cup of coffee has a temperature of 200 degrees Fahrenheit and is placed in a room that has a temperature of 7 degrees Fahrenheit. After 10 minutes, the temperature of the coffee is 150 degrees Fahrenheit. First thing we want to do is find a function that models the temperature of this coffee. Then, what is the temperature after 15 minutes? So if we just let the coffee sit there in a room, nobody touching it, and the temperature of the room never changes. So if we just let the coffee sit there, what is it after 15 minutes? Then we're going to figure out how long will it take for the coffee to be 100 degrees Fahrenheit, which is what I think would be safe to drink. And then D, we're going to graph it and then kind of just explain what this graph looks like real quick. All right, so part A, let's go ahead, let's find our function. So recall that Newton's law of cooling is the final temperature is equal to the initial temperature times e to the negative kt plus the temperature of the surroundings. Now, within the problem, and it's going to be kind of hard for me to do this, so I'm going to kind of scroll up as much as I can. There we go. I think that'll be okay. So T of T is going to equal, well, we know the coffee was initially 200 degrees Fahrenheit, all right? And we know the temperature of the surroundings was 70 degrees, okay? So, sorry. So what we're going to have to do here is figure out D sub 0. So let me erase this real quick. All right, so D sub 0 is going to be the change in temperature. Now, initially, we know it was 200 degrees Fahrenheit, but that's going to change as time progresses. So D sub 0 is really 130. So in other words, what you have is you have the temperature initially and the temperature of the surroundings, and those two together are going to influence the rate of cooling. All right? So so far we have our model. Temperature, or the final temperature, is going to equal to 130 e to the negative kt, all right, plus 70, okay? But now the question becomes, how do we actually find K? Well, there was something given to us in this problem, and anytime you do Newton's law of cooling, you're always going to have to find this, which is, we know that after 10 minutes, that temperature of the coffee was about 150 degrees, okay? So we're going to use that to our advantage, all right? So T equals 15 minutes, and the temperature of that coffee at that time was 150 degrees. So let's make our substitutions here. And what we're going to do is we're just going to solve this equation right here. So let's go ahead and subtract 70 from both sides. That's going to give us 80 equals 130 e to the negative, I guess I'll just write e to the negative 10k. Divide both sides by 130. That's going to give us e to the negative 10k is going to be 8 over 13. Now I'll take the natural log of both sides. By doing that, it's going to let me take my exponent and pull it out in front. We know the ln of e is 1, so I'm just going to leave it like this. And then finally, I'm going to divide both sides by -10 to give me k, and k is approximately, if you use a calculator, 0.04855. The more decimal places you have for k, the better approximation you're going to get. So make sure you keep at least 5 decimal places. All right, and right there, we can finally write our proper model. The temperature of the coffee at any time t is going to equal 130 e to the negative 0.04855 t plus the temperature of the surroundings, which is 70. The one thing I do want to go over again real quick is I want to go over this d sub 0 thing again. This d sub 0, it's going to be like that initial temperature, and maybe I didn't explain that correctly. So that's why I want to go back over this. There is going to be a difference in temperature, and that difference in temperature, how great that difference is going to directly influence, let me get out a highlighter here. It'll directly influence K, which is that rate at which something cools. All right? So you always got to make sure that you find D sub 0 first. So all it is just it's just the change in temperature. That's all it is. Okay? So if you could imagine, if the room was much colder, your difference would be much greater, and it would actually cool down faster than if the two temperatures were similar in temperature. So that's why if you place something very hot in your freezer, it'll actually cool down faster than if you place something that's room temperature in your freezer. It won't cool down as fast. All right? So part A is done. Part B, what is the temperature after 15 minutes? All right, so let me write that down. Temp after 15 minutes. Well, this is just, all this is nothing more than just plug and chug, which is really, really nice for us. So the temperature after 15 minutes is going to equal 130 e to the negative 0.04855 times 15 plus 70. So the temperature after 15 minutes is going to be approximately 133 degrees Fahrenheit. Now, you coffee aficionados, you could just let me know if that's a good temperature to drink. Like I said, I have no idea. All right. Now, part C, I'm going to scroll back up so I can look at it. Part C is that special one. How long until the coffee is 100 degrees Fahrenheit? So how long until coffee is 100 degrees Fahrenheit? Okay? So what we want to know is we know the final temperature of the coffee is 100 degrees Fahrenheit. What we want to know is how long is it going to take? So 100 equals 130 e to the negative 0.04855 t plus 70. So we're solving for t, which is our variable, which means eventually we're going to have to take the natural log of both sides. So let's go ahead. Let's isolate the exponential. We're going to subtract 70 from both sides. That's going to give me 30 equals 130 e to the negative 0.04855 t. Divide both sides by 130. All right. That is going to give me e to the negative 0.04855 t. On the other side, it's going to be 3 over 13. I just reduce it, divide it by 10. Finally, we take the natural log of both sides. And I'm just going to write negative 0.04855 t because we know we're going to pull it out in front. ln of e is 1. And then finally, divide both sides of the equation by negative 0.04855. And t equals 30.2 minutes. So if you just let it sit there, in about a half hour, the coffee would be 100 degrees Fahrenheit, which I think is pretty safe to drink. All right. Now, finally, part D. Part D was to graph and then interpret it. All right. So I just want us to think about this before I actually graph it. We know that we have coffee cooling down. So T on the x-axis is going to be time, and then capital T of T is going to be the temperature at any time, and we know it's going to look something like this. Actually, let me do it like this. All right. You're going to notice that this is going to start to level off, and I want you to think about, well, what is it leveling off to? Now, if you think about it, the coffee's hot, and you put it in a room that's 70 degrees. All right. So this line that I just drew here, and I'm going to really draw it very specially now. Especially, that's not even a word. What I'm going to do is I'm going to do this. I'm going to draw this asymptote. This should be the line T equals 70 because the room is 70 degrees. That coffee is not going to go any colder or any cooler than 70 degrees. All right. So let's go ahead and let's just model this. So we're going to pull Desmos out real quick. All right, and let's go ahead and graph. So we're going to type in 130 e, raise it to the negative 0.04855 x, because you got to use x in Desmos, plus 70. And I will zoom out here. And there is what we would expect to find, a decaying exponential. And then if I graph y equals 70, notice that is going to be the asymptote here that we were looking for. So I'll just zoom in here a little bit. And that looks pretty good to me. And like I said, if you just scroll to the right, notice it's going to approach 70 degrees. But it never, ever gets below 70 degrees. Mathematically now. Like I said, models just give us an idea on what is going to happen. It doesn't mean it's going to be perfect. We know that eventually, if we put a thermometer in this coffee and it sat in this 70-degree room for 4 days, it's going to be 70 degrees. But technically, we really got to be careful about the thermometer we're using. If it only reads 2 degrees, like 70, then it's going to say 70. But it could be 70.1 or 70.01 or 70.001. So theoretically, this is what's going to happen. Actually, we know temperature gets to 70 degrees. So I hope this helped, and I'll do pH scales in the next videos. That'll be a part 2. So see you in a bit. Bye.